So for this section, we're going to talk about limits, asymptotes, and continuity. So this is a fairly long flipped class video, so you might want to take a couple of sit-down sessions to watch this rather than trying to do it all in one go. Or you might take a couple of times to watch through it to make sure you absorb everything that's in this video. All of the stuff in this is very important to understanding what's coming next in calculus class. So let's go ahead and get started with this. So remember that we saw in the previous section that if we wanted to get the instantaneous velocity of something at a time t equals t0, what we could do is we could take average velocities around that time, which turned out to be the slopes of the secant lines, and the smaller the intervals we looked at, the better the approximation would be. And similarly, those secant lines would give us an approximation for the slope of the tangent line. So we saw how to do this with tables by looking at values that got closer and closer together. In this section, we want to kind of formalize that process so we can actually calculate these things exactly. So we'll come back to that topic of speeds and slopes of tangent lines more in the next section. For this section, we're going to talk about mainly just the machinery that will be needed for the next section for this. So the idea is we should be able to look at these slopes of secant lines like this, and we should be able to calculate these exactly rather than just having to use tables and kind of getting a better and better approximation as we go and having to guess the values. And so one warning here, and this won't come up so much usually in this section and the next, it actually ends up happening later in the semester when you've kind of forgotten about what's going on here. It looks like as t gets closer to t0, well, as t gets closer to t0, the top there gets close to 0 because f of t gets close to f of t0. And so a lot of times people will say, oh, the limit as t goes to t0 of this thing is 0. But we have to be careful of that because the bottom is also getting close to 0. And we saw several examples in the previous section where this doesn't get closer to 0. This is the slopes of secant lines. And as the intervals got smaller, it became closer to the slope of the tangent line. And a lot of times that is not 0. So just be careful of this later in the semester. There'll be several times where this limit will come up. And it's easy to make the mistake of thinking it's going to be equal to 0. So normally a definition of a limit involves something called epsilons and deltas, and it's quite technical. For this calculus course, we don't need that. We're going to go with kind of a more intuitive definition. And if you're interested in the more rigorous definition, of course, you can read that in the textbook or find a video online dealing with that. For us, what we're going to say is if we have some function defined on some interval a, b, and we're going to take any number between a and b, and if this function is defined at all of the values of the interval except for possibly the value c, so it can be the case that f is not defined at c, we say that the limit of f of x as x approaches c is equal to some number L if as x gets closer and closer to c, the values of f of x get closer and closer to L. And if this is the case, we write limit as x goes to c of f of x is equal to L. So one thing to keep in mind here that we have to be careful of, when we say x is getting closer to c, it could be coming from being bigger than c or from being smaller than c. And for the limit to exist, it has to be true coming from both directions. Okay, so let's take a simple example to start with. So let's say f of x is equal to x squared plus 2. And let's suppose we want to take the limit as x goes to 1 of f of x. So we want to say as x gets close to 1, what happens to f of x? So here we can see some values on this graph coming from the left and the right. So this red dot as our x values get closer and closer to c. We're tracing these along the curve, and we can see that the y value there is the x's get close to 1 is getting close to 3. So that would lead us to guess here that the limit as x goes to 1 of f of x should be equal to 3. Instead of a graph, we could also use a table of values. So if we plug in values coming from the left and from the right, we see we're getting closer and closer to 3 in that regard as well. So the table also tells us that the limit as x goes to 1 of f of x should be equal to 3. And in this case, it's a particularly nice case because f of x is actually just defined at x equals 1. So when the function is defined there, you can just go ahead and plug the value in, assuming it's a nice function, and that will be the limit. It can be the case that's defined there, and that's not the limit. But for us, since f is just a polynomial, that will work. And we see if we plug in 1 here, we do actually get 3. So this function's a little different. In this case, if we want to look at the limit as x goes to 2, the first thing to note is that f is not defined at 2. So if I were to plug 2 in here, I would get 2 minus 2 in the denominator, which is 0. And we know we're not allowed to have zeros in the denominator. So this function is defined everywhere except for x is equal to 2. But we can still look at the limit as x gets close to 2. So again, we look at a graph here. Notice there's an open circle there at 2 because it's not defined at 2. And now as my red dots come from the left and the right, even though they can't ever get to x is equal to 2, we can see the y values are getting closer and closer to 4. So that leads us to believe that the limit here should be 4. Again, we can also check this with the table. It's important to be able to think of these things graphically and in terms of tables. So again, as we plug in values coming from the left-hand side and the right-hand side, we see we're getting closer and closer to 4. So the graph and the table both let us think that this should be 4. Let's see if we can figure out how to actually show that. So if x is any value that's not equal to 2, we can go ahead and factor the top there. And since x is not equal to 2, that x minus 2 is just some number. It's not equal to 0, so we can cancel that out. And so for any value of x that's not equal to 2, f of x is just x plus 2. So in that case, again, we can just plug the value in for x, and we get 2 plus 2, which is 4, just like we expected it to be. And there are a couple steps in here we haven't justified yet, but that's okay. In the first semester calculus class, we're not always going to justify everything. Sometimes we're just going to accept things work like they should work. So let's consider another example now. This is a piecewise defined function. So that means this function is defined in the interval from 0 to 2, not including 2. But between 0 and 1, we have that the function is 1 minus x over 2. And for 1 to 2, where we include 1 but not 2, it's just defined to be x. So we can ask, well, what's happening at that middle point there where the piecewise function is kind of coming together? So where we're having the first line 1 minus x over 2, and then the second line x. What happens in that spot when they kind of come together? So if we look at a graph of this, we see if we're coming from the left-hand side, the little red circle is getting closer and closer to 1/2. But if I come from the right-hand side, it's getting closer and closer to 1. So we're not going to any particular value here. If I'm close coming from the left, I'm getting close to 1/2. If I'm close coming from the right, I'm getting close to 1. So there's no value that L can be here that the function has as a limit, because it would have to be 1 and 1/2, and it can't be two things at once. So what we can, though, do is we can say, rather than looking at the entire limit as x goes to 1, we can consider just what happens as it comes from the left, and we can consider what happens coming from the right. So we indicate this with, if we're coming from the left, we put a little negative sign above the 1 to indicate it's coming from the negative side of 1. And in this case, we saw in the previous picture that it's getting close to 1/2. And if we, so that's called the left-hand limit, and we can do the same thing if we come from the right. It would go to 1. And notice we put a plus there because it's coming from bigger values than 1 going towards 1. So that's referred to the right-hand limit. So just like we were doing limits before, where we had to consider both sides, for left and right-hand limits, we do the same thing. We just only look at one side. And the important result here is that the limit as x goes to a is L if and only if it's L coming from the left and the right. So as our previous example showed, we could have the limit existing from the left and a limit existing from the right, and those could not be equal. And then we don't have an overall limit as x goes to a in that case. Okay, let's consider another type of function now. Let's look at f of x as 1 over x minus 2 squared. And let's look at the limit as x goes to 2. So notice here this function is not defined at 2, because if I plugged in a 2, I would get 2 minus 2 squared in the bottom, and that would give me a 0 in the denominator, and that's not allowed. But we can still ask what's happening as x gets close to 2. So if we graph this, we see that this isn't going to have any particular number, because if I'm going towards 2 from the left, this graph just keeps getting bigger and bigger and bigger. And same thing if it comes from the right-hand side. It just keeps getting bigger and bigger and bigger as it gets close to 2. So this limit isn't going to be equal to L for any particular number L. So the limit does not exist. But this isn't quite as bad as the previous example, where from one side it went to 1/2 and the other side it went to 1. From either side, it's just getting bigger and bigger and bigger. So in this case, what we say is the limit diverges to infinity, and we'll just write it as limit as x goes to 2 of f of x is equal to infinity. So we can still say what's happening to the function as x gets close to 2, even if it's not getting close to some particular number. And if this is the case, we refer to the line x equals 2 as a vertical asymptote of the function f of x. So vertical asymptotes often occur when you have a 0 in the denominator. So if you have coming from the right or the left that the function is plus or minus infinity, then we say x equals a is a vertical asymptote. So it could be going to infinity, could be going to minus infinity, and it could be going to plus infinity from one side and negative infinity the other side. Okay, so here's an example. If I look at f of x is equal to 1 over x, this is the graph of that. And so we see as we come from the left-hand side going towards 0, our function goes towards negative infinity. And if I'm coming from the right-hand side going towards 0, I go towards positive infinity. So this tells me that x equals 0 is a vertical asymptote of the function f of x is equal to 1 over x. Now there's a bunch of limit laws that we're going to end up using in this course, and we would like to, if we were in a higher level math course, we would prove all of these are true. But for us, we're going to just go ahead and accept that these work out how we want them to, and we'll just use them without actually proving they're all true. But you do need to remember all of these. So if we have that a function is a constant, the limit as x goes to a of the constant c is just c. So remember, the limit is saying what happens to the function as x is getting close to a. Well, if your function is constant, it's not moving at all no matter what x is, so it's always just going to be c. Obviously, if x is getting close to a, then x is getting close to a, so that makes sense. If we have any positive integer, and we're looking at the limit as x goes to a of x to the n, we can just go ahead and plug that a in for x and just get a to the n. So for example, if we're looking at as x goes to negative 3 of x cubed, we just plug that negative 3 in for x, and we look at negative 3 cubed, which is negative 27. Okay, if we take a constant c, and we happen to know that the limit as x goes to a of f of x is L, and the limit as x goes to a of g of x is m, then if I look at the sum of the limit of the sum of the functions, or this difference of the functions, the result is just the sum or difference of the limits of the functions themselves. So basically, you can distribute the limit over the sum or difference. If I have a constant times a function, I can just kind of pull that constant out front of the limit and then just take the limit of the function. If I have the limit of a product of functions, that's just the product of the limits. And if the limit of g is not 0, then the limit of the quotients is just the quotient of the limits. And if I take the power of any of the function, it's just the power of the limits. And you can think of this as just taking number 3 there, the product, and just applying it lots of times with a single function. And finally, if I take a square root, I can bring the limit under the square root as well, as long as that L is positive. Or if, it depends upon if it's a cube root, then it doesn't have to be positive. Just so long as that nth root makes sense, basically. So let's see an example of how we can use this to calculate a limit algebraically. So let's look at this function as x goes to -2 of x to the 4th minus 2 over 2x squared minus 3x plus 2. So first of all, we can distribute the limit to the top and the bottom so that we have the quotient of the limits. Now we can distribute it over the sums and differences and factor out the constants. And then we can just plug in for the powers there. So I get a -2 to the 4th. We know the limit of a constant is that constant. And then similarly for the bottom. And when we simplify this, we get 7/8. So we can see this is much easier than having to graph the function and look at values and then take a table of values and then kind of guess what's happening here. In this case, it's once we accept those limit laws, this is very easy to just do algebraically. Okay, so you should probably pause the video here, and hopefully you've written down the limit laws on the previous slide. If not, maybe pause and go back and write all those limit laws down, and then go through and make sure you can justify what laws we're using at each step to get this limit. Okay, so here's another rule that's super useful. So if f of x is equal to g of x when x is not equal to a, then the limit as x goes to a of f of x equals the limit as x goes to a of g of x. We actually already used this before when we looked at the x squared minus 4 over x minus 2 example. Okay, so we'll see another example of this next, just like the one we saw before. So let's go ahead and calculate the slope of the tangent line at f of x equals x cubed at the point 2, 8. So remember, the slope of the tangent line at x equals at the point 2, 8 is given by this limit as x goes to 2 of x cubed minus 2 cubed over x minus 2. And so we're going to come back to spend a little more time on these types of limits next section, but for now, let's go ahead and calculate this. So notice I can factor in x minus 2 out of the top. Of course, this limit here, x cubed minus 2 cubed over x minus 2, that function, x cubed minus 2 cubed over x minus 2, that's not defined at x equals 2. But notice that I can factor that x minus 2 out, and then I can cancel, so I get x squared plus 2x plus 4. And so now, as long as we're not looking at the value x equals 2, x cubed minus 2 cubed over x minus 2 is exactly equal to x squared plus 2x plus 4. So this is using that limit law that we saw on the previous slide. And now we can use our rules to just go ahead and plug that 2 in, and we get 12 here. Now we could also do this by looking at the limit as h goes to 0 of 2 plus h cubed minus 2 cubed over h. And so to see why this is the case, just think of we're letting x be getting close to 2. So just write x is equal to 2 plus h. And notice if x is getting close to 2 and x is equal to 2 plus h, then that h has to be getting close to 0. So that's what we're doing here. And then on the bottom, we'd have 2 plus h minus 2, which just gives me h. And a lot of times this way of calculating it will be easier because we won't have to figure out how to factor the top part. So in this case, we just go ahead and FOIL that 2 plus h cubed out, and that gives me 8 plus 12h plus 6h squared plus h cubed. You can go ahead and pause the video and check that if you like. Now notice that 8 at the beginning and the negative 8 at the end cancel out. And so I have in the top 12h plus 6h squared plus h cubed. I can factor an h out of that. give me h times the quantity of 12 plus 6h plus h squared all over h. Now I can cancel the h that I factored out on the top with the h in the bottom, and I just get 12 plus 6h plus h squared. As h goes to 0, that's 6h plus h squared goes to 0, and I'm just left with 12. So I get the same answer as I got on the previous slide. So it's probably a good point here to stop and maybe draw some pictures to understand what this is meaning geometrically. So when you think of this 2 plus h cubed minus 2 cubed over h, try to think about what that means geometrically in terms of slopes of secant lines. So one more limit law that can be useful in calculating limits is the squeeze theorem. So basically what this says is that if f of x is less than g of x is less than h of x, when x is near a, except possibly at x equals a, and if we happen to have the limit as x goes to a of f of x, and the limit as x goes to a of h of x is L, then that limit in between is getting squeezed because the bottom part, the part to the left is going towards L, the part to the right is going towards L, so it's kind of smashed in between and it also has to go towards L. So this is best illustrated with an example to kind of see a picture of what's going on. So if we look at this function, f of x is equal to x times sine of 1 over x. And now this function is definitely not defined at 0 because we have the sine of 1 over x, but we can ask what the limit as x goes to 0 of this function is. So now this is the graph of this function, which looks like a huge mess here. But it also looks like if you were to follow this path going from the left to the right, it does look like it's getting closer and closer to 0. And so what we can use is we know the sine function is always between minus 1 and 1. So if that tells us that minus 1 is less than or equal to sine of 1 over x is less than or equal to 1 for every x except for 0, since our function is not defined there. So if I multiply that inequality by x, I get negative x is less than or equal to x times sine x is less than or equal to x. And now I know that the limit as x goes to 0 of x and negative x is both 0. So squeeze theorem says that that overall limit has to be 0. And if we look at a graph of what's going on here, that the red line y equals x and the also red line y equals minus x, you can see those are smashing that function there and forcing it to go to what those limits are, which is 0. So up to this point, we've talked about limits as x goes to a, where a is some number. We're also going to want to consider the case when a is infinity or negative infinity. So that's what we're going to look at now. So if we let our function be defined on some interval from b to infinity, we say that the limit as x goes to infinity of f of x is equal to L if the values of f get closer and closer to L as x gets bigger and bigger. So let's think about this, an example of this. If I look at the function f of x is equal to 1 over x, as x gets really large, the values of f of x gets closer and closer to 0. So just think of putting some large values in there. F of 10 is 1/10, f of 100 is 1/100th, f of 1 million is 1 over a million. Those are getting to be very, very small. So here's a picture of what's going on for this. We can see it gets very small very fast. So in this case, we would write the limit as x goes to infinity of 1 over x is equal to 0. This is actually a very important limit to remember as well. It will come up often. Let's try another example. Let's let f of x be 2x squared plus 3x plus 1 over 7x squared plus 5. And suppose we want to calculate the limit of this as x goes towards infinity. So let's go ahead and plug in some values, see what's going on. So if I plug in 100, I get about 0.29. If I plug in 1,000, I get about 0.286. If I plug in 10,000, I get about 0.2857. And if I pick some really large number like 10 to the 8th, I got about 0.2857 again. So it seems like a pretty good guess that this limit is about 0.2857. And so we can go ahead and conjecture that that is our limit. But of course we want to calculate this exactly and not just have to conjecture. So let's see if we can figure out a way to prove that our conjecture is true. So we're going to use the limit laws just like before, even though we stated them only for x going towards a number. But if we do this, we can take the top and the bottom, and we'll multiply this function by 1, but we're just going to write 1 in a really funny way. We're going to write it as 1 over x squared divided by 1 over x squared. And I chose the 1 over x squared because that was the highest power in the polynomial in the top and the bottom. So now if I FOIL that 1 over x squared through the top and the bottom, notice the first term, the 2x squared times 1 over x squared, just gives me a 2. 3x times 1 over x squared gives me a 3 over x. And 1 times 1 over x squared gives me 1 over x squared. And similarly on the bottom. And now we can distribute that limit through, and just notice that the limit as x goes to infinity of 3 over x. I can pull that 3 out front, and then that gives me the limit as x goes to 3 times the limit as x goes to infinity of 1 over x, which is 3 times 0. And similarly, the limit as x goes to infinity of 1 over x squared is the square of the limit as x goes to infinity of 1 over x, which is 0 squared, so that's 0. And similarly on the bottom, and so we could get this to be 2/7. And 2/7 is about 0.2857, so this seems to work just like our table suggested it would. And now you might have learned, if you saw limits in high school, that if you have a rational function like this, a ratio of two polynomials, if the degrees are equal, the limit as x goes to infinity is always the coefficients of the highest, the ratio of the coefficients of the highest terms. So that's not going to be acceptable for logic on an exam. So you need to be able to actually go through and show why this limit is 2/7, not just say, oh, well, it's always the coefficients of the highest power. So make sure you understand what was happening here. So now if we have the limit as x goes to infinity of f of x as L, or the limit as x goes to minus infinity of f of x as L, we say the line y equals L is a horizontal asymptote of the function. So in previous examples, we saw y equals 0 is a horizontal asymptote of f of x is 1 over x. And similarly, y equals 2/7 was a horizontal asymptote as the function we just looked at. So let's go ahead and find the horizontal and vertical asymptotes of this function f of x is equal to x squared plus 2 over square root of x to the 4th minus 1. So we'll start with the vertical asymptotes, which in this case are going to be where the function is not defined. So notice we require x to the 4th minus 1 to be bigger than 0 because I have to have positive numbers under a square root and I can't have any zeros in the denominator. And so I need x to the 4th is bigger than 1. And so that happens when minus 1 is less than x is less than 1. Or I mean since we need x to the 4th bigger than 1, the values when it's between minus 1 and 1 are not going to be in our domain because that would give us values of x to the 4th less than 1. So I have a 0 in the denominator when x to the 4th is equal to 1. So this happens exactly when x is equal to plus or minus 1. So that should tell us the vertical asymptote should be at x equals minus 1 and x is equal to 1. So let's find the horizontal asymptotes now. So notice that this is an even function because f of x is equal to f of minus x. So that means the limit as x goes to infinity is going to be the same thing as the limit as x goes to negative infinity. So we only have to do one of the limits and not both of them. So if we calculate this limit, this one's a little trickier than before because we have that square root of x to the 4th minus 1, but we can think of the square root of x to the 4th as kind of like x squared. So we're still going to view this as kind of like a polynomial of x squared over something of x squared as well. And we'll multiply the top and the bottom by 1 over x squared for both of those, and then distribute it through. The trick here is to remember that if I have 1 over x squared, that's the same thing as 1 over square root of x to the 4th. And then we can combine those square roots. And so then I get an x to the fourth minus 1 square root of x to the fourth minus 1 over x to the fourth. And then I can just simplify that by x to the fourth over x to the fourth is 1. And 1 over x to the fourth is 1 over x to the fourth. And now, just like before, we look at where these things, as x goes to infinity, that 2 over x squared goes to 0, and 1 over x to the fourth goes to 0. So here's the algebra we actually used that I just explained. So that told me that I had a horizontal asymptote at y equals 1. And here's a graph of this function. So we see those vertical asymptotes at x equals minus 1 and 1, and the horizontal asymptote at y equals 1. Now, a couple more things we need for this section. The first is the notion of continuity. So the idea you want to keep in mind when you're thinking of continuity is the intuitive one that if you're graphing a function, anywhere where you can graph the function without lifting your pencil or pen up, the function's continuous there. If you have to lift your pencil or pen up, then it's not continuous there. And so a precise definition is that it's continuous at x equals a if the limit as x goes to a of f of x is actually equal to f of a. And one thing to keep in mind here is this means that the function has to actually be defined to be continuous there. So anywhere the function is not defined, it's not continuous at that point. So let's go ahead and look at an example. So it's often easier to state where it's not continuous because it'll usually for the things we'll look at, it'll be very few points. So for instance, if we're looking at this graph, you can start over here to the left where it looks like it's about negative pi where it starts. And if you start tracing this with your pencil, so let's maybe trace it with the cursor here. If we were tracing this along, I can keep drawing it as I'm going just fine until I get to 0. And then you see you have an open circle here at 0. So I have to pick my pencil up and put it back down over here and start drawing again. So it's not going to be continuous at x equals 0. And then I can go all the way to 3, but then I have to stop. I have to pick my pencil up and come up here and then continue drawing until I get 4. So it looks like this is about at pi, so that'll also be discontinuous there. Okay, so here's our two spots where it's discontinuous. Just like the intuitive definition told us. So if we want to state it where it was continuous, we'd say it's continuous starting at minus pi up until we get to 0, and then from 0 until pi, and then from pi until 4. So there's a couple more ways to write this. Let's try another example. So just like the previous one, we could start over here and we keep going. And I see my function has a vertical asymptote at x equals negative 1. So it won't be continuous there. So I pick my pencil up, I start again. And then I can continue going right up until I get to 1. I have to stop, pick it up. Now it's defined here, so I can go down to here. I have to pick it up again and go back up to here and keep drawing. So we see our problems here are at minus 1 and 1. So again, we could rewrite this if we wanted in terms of where it is continuous, though we see these examples, it was easier to say where it wasn't continuous. And finally, a theorem that's really important to the theory of calculus, but won't really come up much in this level of a course, but it's important for you to at least see it. So this is called the intermediate value theorem. So suppose I have a continuous function on an interval ab, and let's let n be any number between f of a and f of b. Then there's some value of c between a and b, so that f of c is equal to n. Now that looks pretty complicated, but let's just look at some pictures here to see what's going on. So here's our function, y equals f of x. And notice this is continuous between a and b because I can start here at f of a, and I can trace along until I get to where f of b is, and I didn't have to pick up my pencil at all. So then let's see, well, we have f of a is over here, and f of b is here, and I pick any number between these two numbers. And so notice, since I don't have to pick my pencil up, if I trace across from where the n is, I'm going to have to hit this at some point, because otherwise I'd have to pick my pencil up to avoid it and then keep going. Well, wherever I happen to hit this at, we just drop down to the x-axis and see that's where my c value is. And just notice now that f of c is exactly equal to n. So that's all the theorem is saying, is if I pick any number between these two, since I don't pick my pencil up at all as I go through here, no matter where the number is, there has to be somewhere where it's the value of f at some value c. So it's pretty intuitively clear. It's not so easy to actually prove this, but once we draw the picture, we can understand why it's true. So if it comes up later in the course that we need it, we can accept that it's true just based upon the picture we saw.